This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, I am not going to tell you the entire history of cosmology. We're going to get straight to the point. The point is the expanding universe and the geometry of the expanding universe. Well, let's back off for a minute and discuss what it is, where it is we want to go. I wanted to teach you the basics of modern cosmology, and the basics of modern cosmology consist of a handful of things, not a lot, but of course the things which went into the discoveries, especially the observational discoveries, were a lot more than I'm going to tell you. But basically, we're going to take, go to the end of the story to a large extent and say, what is it that we know now? We're going to start with the basic Big Bang theory. We're not going to go back in time before there was a Big Bang theory. We're going to start with the basic Big Bang theory, the three possible versions of it. We're going to do it from 2 points of view and then match them and see how they relate. The first is just thinking about geometry, the general theory of relativity that we discussed last year. Now, we're not going to have to know very much about the general theory of relativity, just some very, very simple things. And we're going to talk about expanding space. We're going to talk about the Hubble law of recession, the relation between velocity and distance, and so forth. We're going to derive that from some simple principles. We'll state what the simple principles of cosmology are, of Big Bang cosmology, and we'll work out some examples of expanding universes, the geometry of them. Not the physics of them. This is the geometry of them. The physics is driven by energy and momentum and other dynamical things. To get a handle on that, I don't know if we'll do it this week, but next week, either this week or next week, we'll move on to the Newtonian, F equals ma cosmology. F equals ma cosmology takes us a long way, and we're going to see some connections between the geometry and the F equals ma version of cosmology, what Newton would have understood as cosmology. And then we're going to put them together into a single package called Friedman-Robertson-Walker FRW cosmology. That will take us a couple of weeks. From there, we'll address some other questions. What is inflation? What is the inflationary theory of cosmology? What is dark energy? What is dark matter? How are they different? The cosmological constant, which is dark energy, the current accelerated expansion of the universe, and then perhaps we'll move on to some more modern esoteric subjects, such as why do physicists think perhaps there's much more to the universe than we can see, but more than we ever can see, and the idea of a multiverse. And I'm not sure what else. We'll fill in some details as we go along. If there are particular things you want me to discuss, I'll do it as usual. But let's get started. Okay, let's begin just with the idea of space, and the simplest possible space, one-dimensional space for simplicity. Then it'll immediately add 2 more dimensions. Space, not space-time. And it's just good old x-axis. The x-axis, imagine it goes on indefinitely, both in the left direction and the right direction. And imagine embedded in it are some objects which are equally spaced. They're embedded in the space, and I'm going to give them a name now. They're called galaxies, okay? One-dimensional galaxies. But they're just particles or objects which are embedded in this line. Okay. Now, the first question is, let's label a line with a coordinate, and let's label a line with a coordinate which in this particular case just measures off, this is x equals 0, and let's use the presence of these galaxies to define a coordinate so that by definition the next galaxy over is x equals 1. Obviously this is an enormous idealization where I have the galaxies perfectly uniformly spaced. This is of course not the case in the real world. Incidentally, for those who may wonder, the world is three-dimensional, not one-dimensional. So that's a further idealization or a further fiction. X equals 2. This is worse than flat land. This is line land. Here's x equals minus 1. Whoops, minus 1. Here's x equals minus 2. And roughly speaking, these coordinates simply label which galaxy we're talking about. We could think of them as the name of the galaxy. This galaxy is called x equals 2. This one is called x equals 1. They're just labels which move with the galaxies if the galaxies are moving, if they're spreading apart, if they're coming together. This coordinate just is attached to the galaxy. All right, now, how far is it from, let's say, x equals 0 to x equals 1? Well, it's some distance. It's not 1 unit. These are just the names of these points. These don't say anything about distance. I'm going to assume they're equally spaced. But what is the spacing? I haven't told you what the spacing between them is in meters, or kilometers, or light years. Pick your favorite unit. For the time being, the units aren't important. But, what's that? Well, they are one galaxy apart if by galaxies we mean the distance between galaxies.
Units of the size of each galaxy.
Well, we could use the size of each galaxy, but we could use, well, I don't want to use the size of the galaxy because it's going to raise a question that I don't, but let's say meters, meter sticks, we measure them off. And I'm going to call the distance between x equals 0 and x equals 1 in meters or whatever definite units we use. The reason I don't want to use the size of galaxies is because the size of galaxies changes with time. They tend to contract, so I don't want to get into that. But just good old meter sticks, good solid meter sticks that don't change with time. And let's say the distance between x equals 0 and x equals 1, let's just call it a. A, that's it. What's the distance between x equals 0 and x equals 2? Twice a, because I've assumed that they're really equally spaced. In particular, the distance between any 2 points is just, let's call it delta x. That's the difference in x times a. A times the difference in x, if it's x equals 2 minus x equals 0, then it's 2a. This is the distance between any 2 galaxies. Delta x means the difference of x. This could be x equals, let's see, 1, 2, 3, 4, 5. The distance between the galaxy called x equals 5 and the galaxy called x equals 1, that's delta x equals 4 times a is the distance. A times 4 is the same as 4 times a. What about the distance between x equals 3 and x equals minus 1? That's also 4 times a. And so that's the notation. That's the notational thing we're going to do. Distance is the coordinate difference times a, and a has a name. It's called the scale factor. It's called the scale factor. Its name is the scale factor. Okay? Now, the galaxies may be moving. Right? Think of this line, imagine this line for the moment as an elastic thread, an infinite elastic thread, but about infinite is too big for right now, a very large elastic thread, and there are 2 giants at the end, and the 2 giants are having fun with the people in this universe, and they're pulling, maybe they also even allow it to go the other way, they change the total length of the world, so to speak. Just by pulling on this thread and stretching it, contracting it, doing whatever it is they decide to do, mostly stretch it, but for the time being. What does that mean about A? That simply means that A depends on time. The distance between two neighboring galaxies will depend on time, exactly as it would. Think of rubber band. Cut the rubber band open. I don't want it to be double. And think about stretching. And instead of galaxies, think about the rubber molecules. You stretch, that increases the distance between neighboring molecules. You contract it, that decreases the distance. And so in that way, in general, A is a function of time in this world with these giants who are pulling on the end of the string. This is not string theory, incidentally. Nothing to do with string theory. Not yet, anyway. I've heard that in Berkeley, there's a restaurant called Noodle Theory. Can anybody confirm that? It's true? Noodle Theory, okay. Okay, so this is the universe, and the universe is such that, first of all, it is homogeneous. Homogeneous means equal spacing. That's all. Right? Equal spacing, it's everywhere is the same, so to speak. Every one of these galaxies looks at its neighbor and says, you are a certain number of meters away. A galaxy over here sees the same thing as a galaxy over here, and so forth. That's the term homogeneous. Everywhere is the same, equal spacing, but the spacing itself, imagine that it's time dependent. Okay, let's now calculate the rate at which the distance between two galaxies grows or shrinks. The rate at which the distance changes with time. Let's calculate it. There's another word for the rate at which distance changes. What? Velocity, right. Actually speed, but velocity, right, velocity. So when I say I'm calculating the rate at which the galaxy at x equals 4 moves or increases relative to x equals 1, I could say it another way. I'm calculating the velocity of x equals 4 relative to x equals 1. But I don't just want to call it the velocity. I want to call it the velocity of one point relative to another. All right, we know what the distance is. Here's the distance. It's a times delta x. Now we're taking two fixed galaxies. Two fixed galaxies. This one over here and this one over here. We're not going to change those galaxies, and that means that delta x is not going to change with time. We've just fixed the two galaxies we want to talk about. But what does change with time? A. All right, so what is the rate at which d increases with time? It's just d dot, and for those who haven't been, who are new to this class, dot always means time derivative, derivative with respect to time, d by dt. That's what a dot means, derivative with respect to time. I'll use that notation, and it means the rate at which the thing is changing with time. The rate at which d is changing with time, delta x is not increasing or decreasing, so d dot is delta x, that's unchanged, but a is changing with time, so a dot. The time rate of change of a product like this, if one of the factors is not changing, is just that factor times the time derivative of the other one. So this is the rate at which d changes with time. Let's call it d of delta x, the distance between 2 points separated by delta x. That's just this. Now I'm going to do, and what do we call this? We call this the velocity, the relative velocity between the 2 points. It's the velocity that the astronomer at x equals 1 would see x equals 5 moving away from him or moving toward him. It's also the velocity that x equals 5 would see of x1, either moving away or coming closer. It depends on whether the derivative is positive or negative, whether they're growing larger or distant, less, whether they're approaching or receding. All right, so let's write this, and now I'm going to write a totally unnecessary step. I'm going to divide this and multiply it by A. Physicists and mathematicians are always dividing and multiplying by the same thing, and you think, why bother? Well, let's look at it. Here's A times delta x. What is that? That's D. Okay? So I can rewrite this as A dot over A. That's the ratio of the rate of change of A to A itself times the distance. Now I've discovered something interesting. The velocity of recession, well, I haven't discovered anything interesting yet, but I will have discovered something interesting in a moment. Does A dot and A depend on which galaxies I'm talking about? No. A and A dot are the same for every galaxy. A in particular. A is just the distance between neighboring galaxies, but it doesn't depend on which galaxy we're talking about. So A is the same for everybody, the scale factor. It's a universal idea which everybody agrees about what the distance to his neighbor is. All right? It changes with time, but A dot over A does not depend on X. It doesn't depend on which galaxy we're talking about. And what this equation then says is the velocity between 2 points is proportional to something which does not depend on which galaxy we're talking about, A dot over A, we're going to give it another name in a moment, times the distance between them. Anybody know what the name of A dot over A is? The Hubble constant. The Hubble constant. Velocity is proportional to distance, is what this says, with a number in there, A dot over A. Now, is this necessarily constant if the universe is expanding and contracting or doing whatever the devil these giants have decided to do? Is A dot over A a constant? No, it changes with time. Right? But it doesn't change with position. It's a constant in the sense that it's the same everywhere, but it is not a constant in the sense that it does not depend on time. So the Hubble constant, the thing which I prefer to call it the Hubble parameter. Calling it constant makes you think it's like the electric charge of an electron or something else like that it really doesn't depend on anything. No, the Hubble constant is a function of time, but it's not a function of which galaxy we're talking about. All right? So, what does this say? It simply says the further apart two galaxies are, by that I mean further apart in real distance, the faster they will be moving apart. I say apart, but again, I could be more talking about coming together. And the factor of proportionality is the Hubble constant. Well, among other things, it says that if you look out, if an observer over here looks out to more distant galaxies, the further away he looks, the faster he will be seeing them move. If he looks at his closest neighbor, he'll see him moving away from him perhaps at a certain rate. If he looks at the second nearest neighbor, he will see him moving a little bit faster. If he sees the third nearest neighbor, he will see him moving yet faster. The further away he looks, the faster that will be moving to the right. The same is true. There's nothing in this which has focused attention on x equals 0 or x equals 1. It's the relative separation of two things which are entirely symmetric, and it's the same everywhere. So there's no notion of a center to this line. All points are the same as every other point, but every pair of points are increasing their distance with a velocity that's proportional to h times d. That's the Hubble law. Now, there's nothing especially one-dimensional about this. Let's do it in more dimensions. Any questions about the meaning of this formula?
Yeah, if the galaxies are far enough apart, then they are going faster than the speed of light.
Right. That will play a very important role in cosmology. Right. You know, what you're saying is correct. And we will come back to that for sure. It's one of the most important things. Okay. One other thing. If these, again, Alice and Bob, this is Alice's galaxy, this is Bob's galaxy. Alice and Bob are sending each other messages with light waves or whatever. The faster Bob moves off to the right, the more Doppler shift. Again, they're sending their messages with standard message senders made in the same factory of exactly the same kind. So they're sending light, if you like, of a very, very definite frequency in their own reference frame. But by the time it gets from Alice's signal, by the time it gets to Bob, the Doppler shift will have reddened that light. Or, yes, reddened it. I'm always going to assume from now on that everything is being stretched and not contracted, at least for the moment. So Bob will detect Alice's message being slowed down, but Alice will also detect Bob's message being slowed down. Everything is entirely symmetric between them. And it's simply the problem of two people moving apart from each other, sending light rays. The faster they move apart, the more redshifted the signal will be. So that's a fact about an expanding universe. The further you are away, the faster you move, and the faster you move, the more Doppler shifted will be messages. Now, the kind of messages that we really have in mind, of course, is messages which are sent at frequencies which are determined by basic underlying physics. The underlying physics might be transitions of atoms from one energy level to another energy level, spectral lines. Spectral lines are good standard frequency or wavelength, what should we call them? They have very definite wavelengths in their own frame of reference. And so, for example, if Alice is sending Bob a particular spectral line from the sodium, from some sodium transition, that will be sent in his frame of reference at the usual frequency of a sodium line. But by the time it gets to Bob over here, it will be reddened or lowered in frequency. One way that Alice can measure the distance to Bob is by monitoring the frequency of the light or the spectral lines that come from Bob's galaxy. The faster he's moving away, the more reddened the frequency will be. So that gives you a tool. Now, we're not going to spend very much time talking about observation, but that gives you a tool, or gives Alice a tool, for measuring the velocity of recession of any galaxy. Okay. That's velocity. How about the distance to any galaxy? Are there various ways? Are there ways of measuring the actual distance to a galaxy? Well, let me give you a very simple, more or less what Hubble actually did. Hubble estimated in his first round of detections, his method for estimating the distance to a galaxy was very simple. If the galaxy was bright and big in the sky, it was close. If it was small and dim, it was far. The dimness of a given size object, well, from the size in the sky and from the brightness, he could estimate the distance. for reasons unknown to anybody, Hubble decided to plot on a plot the distance of a given galaxy that he could see in the sky. Again, pretty much just from the size of it. There are much more sophisticated ways of measuring distance than just by size and brightness. But that's clearly one way to measure the distance. And on the vertical axis, he measured the velocity of the galaxies. Well, first of all, the first thing he discovered is that all of the distant galaxies, now distant to Hubble doesn't mean what we would call distant galaxies today. Hubble, when was Hubble? When did Hubble do these wonderful things? In the 20s sometime. Not 1820, 1920. They used galaxies, yeah. Oh, it's an interesting historical fact that up until, let's see, when was it? I'm not exactly sure. Again, it was Hubble, probably 1920 or something, and then 1917, 1916, I'm not sure when exactly. The idea of a galaxy didn't exist. All we knew about was one bunch of stars, the Milky Way, across the sky, and people spoke of an island universe, that we lived in an island of stars with nothing out further than that. They did discover that there were these blotchy things out there, but it was not recognized that those blotchy things were other island universes, so to speak. It wasn't really until sometime in the middle of the early 20th century that Hubble realized that what he was seeing when he saw these smudges in the sky were collections of stars, that they were collections of huge numbers of stars which rivaled in size and number of stars the Milky Way itself. So that was the first discovery. The universe is filled with galaxies. And then he, as I said, measured the distance of galaxies and the velocity of galaxies. And he discovered, first thing that surprised him, the galaxies are moving away from us. Apart from one or two galaxies which are very close to us, our closest neighbor, in fact, just happens to be moving toward us. It's a more or less accidental fact that it's so close to us that it's sort of trapped by our galaxy's gravity, and it happens to be moving close toward us. What's the name of the closest galaxy? The Andromeda. Right. So the Andromeda is moving toward us. That is more or less an exception. If you look out beyond the Andromeda galaxy to galaxies 3, 4, 5, 6 times further away, or 100 times further away, they're moving away. So that was the first discovery. Almost all the galaxies, and in particular all of the distant galaxies, were moving away from us. Furthermore, they were moving away from us by a velocity which depended on their distance. And when he plotted it, he got a perfect, exact straight line. Nonsense. Of course he didn't get it. He got a mishmash which was all over the place. Error bars. But somehow he looked at this, and whether he was intuiting the right answer, or he was a master of statistics, which I don't think he was, or whatever it was, he drew a straight line through it, and he said, look, velocity is proportional to distance. He actually didn't know why. He had no idea. The simple argument did not exist. It's been explained in an even simpler way than this, but this picture here is correct and really at the heart of the matter. But it was explained by other people just saying, look, why are you surprised that the fastest horse goes the furthest in a race? That if you look at a horse race, expect that the fastest one is gone the furthest. Right? The fastest galaxy is most likely to be the one that's gotten furthest away from you. But that of course, is just it's true, but this is the right way to say it. This is the right way to say it. Velocity is proportional to Hubble constant times d. Now, Hubble was not very good at the time at measuring the distances to the galaxies. This wasn't his own fault. He just had crude tools at the time. And he measured the galaxies as being maybe 10 times closer, I think, than they actually were. So his Hubble constant was off by a bit, like a factor of 10. That had implications. Let me explain why. The bigger the Hubble, that of course meant that the Hubble constant was too big. Too big or too small? Wait, he measured, which way did he measure it?
The reciprocal is the time.
He measured the Hubble constant being too big, as I remember. Yeah. He measured the Hubble constant being too big by a factor of 10. Now that meant that his estimate, for example, of this galaxy moving away was 10 times too big. Not that the velocity was correct, but the estimate of the Hubble constant itself was 10 times too big. It took a while to correct it. We're going to discover another interpretation of the Hubble constant. It's basically 1 over the age of the universe. I will tell you why later, not right now. So he had misestimated the age of the universe by a factor of 10. What's that? It's really hard to tell how far, and the more sophisticated tools came into play, but he misestimated things by a factor of 10, but corrected them later. He corrected them. In any case, that's the Hubble law. It's very, very central. I said we can also do the same thing with more dimensions. Let's take 2 dimensions instead of 1 dimension, just for simplicity, x and y. And again, make a grid. Of course, it's nonsense to say that the galaxies are at the corners of the grid, but that's an extreme idealization. But let's imagine galaxies at the corners of the grid. Then every galaxy is labeled with 2 names, a first name and a last name, x and y. And x and y stick with the galaxy. X and y of a galaxy doesn't change with time. It's just a label that labels the galaxy. But the distance between neighbors is again called a in both directions. That brings up an interesting question. Why is it, do we know that the separation between galaxies in this grid model, we could ask, how do we know that the separation between galaxies along the x-axis is the same as the separation between galaxies along the y-axis? Do we know? What do we know about it? Well, supposing the galaxies were not equally spaced, or not that they were equally spaced, but they were more crowded in the x direction than they were in the y direction. At the corners like that. When we look out into the sky, we would discover that things are different along the y-axis than they are along the x-axis. We'd look out along the x-axis and see very crowded galaxies. We'd look along the y-axis and discover they were very, very separated. We don't. We see the same distribution of galaxies pretty much in every direction in the sky. There's a principle involved. It's not a principle. It's actually just a name for that fact. It is called the isotropy of the universe. 2 basic names. The homogeneity of the universe. That means everywhere is the same. Now, this is everywhere is the same, at least on a scale larger than the distance between these galaxies. Looked at on a bigger scale, we would say every place is the same as every other place. Everybody has a couple of neighbors around them, and that's all. And every place is the same as every other place. This here is also homogeneous. This place is the same as this place, or has the same properties as this place over here. This one is the same as this one. There's no sense in which this one over here is special, no different than that one, no different than that one. But there is something different about this than this. It has to do with angles in the sky rather than positions. It's not isotropic. It isn't the same in every direction. It's the same in every place, but it isn't the same in every direction. There's a directionality to this, a directional bias. When we look in the sky, we don't see different things in different directions. Of course, that's not entirely true. I mean, when I look up, I see something different than when I look down. When I look on a scale of our galaxy, if I look into the plane of the galaxy, I see the Milky Way. If I look out of the plane of the galaxy, I see a much darker sky. But on a scale bigger than a few hundred galaxies, on a scale bigger than a few hundred galaxies, the sky looks the same in every direction. So the principle is called homogeneity and isotropy. Now, how well do we really know that the universe is, or how well did Hubble or the people at that time really know that the universe was homogeneous? And the answer is not very well at all. They were able to look through telescopes only to a minute fraction of what we can see today. So really, there was no good reason to believe that the universe was homogeneous on scales much bigger than they could see. Nevertheless, all cosmologists assumed it, and it turned out to be essentially correct, that the universe is homogeneous and isotropic, same in every direction, same in every place. That makes life simple, much simpler than if it was just randomly different in different places. Okay, where were we? Yeah, let's come back now to 2 dimensions. And the spacing of galaxies along the x-axis and the y-axis, the grid size is the same. What's the distance between 2 galaxies separated by distance delta x along the x-axis and delta y along the y-axis? Okay. If anybody want to shoot at it? What the distance is? Square root of, this is Pythagorean theorem. Well, first of all, what's the distance along the x-axis? It's a times delta x. The distance along the y-axis, in other words, if we took 2 galaxies, one over here and one over here, this is the distance. What's that?
Still a times the distance.
Yeah. A times the delta x.
No, I mean, the whole thing just magnifies by a.
Yeah. Yeah, that's right. But let's write it down anyway. Let's go through the steps. The distance along the x-axis is a times delta x. The distance along the y-axis is a times delta y. And then using the Pythagorean theorem, the distance between them is just d is equal to the square root of delta x squared times a squared plus delta y squared times a squared. And now we can factor the a squared out of the square root. And again, as Michael says, it's just proportional to a. It's proportional to a, the distance. And now instead of just simply delta x, it's the square root of delta x squared plus delta y squared. What would happen if there was a 3rd dimension? Plus delta z squared. That's the 3-dimensional Pythagoras theorem, which I don't know if Pythagoras knew or if he didn't know. Okay, that's the distance. What's the velocity between these 2 points? One over here and one out here somewheres? It's just the time derivative of this. All right? So the velocity is given by the same square root, which I won't bother to write, times the time derivative of a dot. That's the velocity of recession. And now we just multiply it and divide it by a over a. Same trick as before. And recognize that a times the square root is just the distance. So we get exactly the same formula as before. Distance times Hubble constant. The Hubble constant doesn't depend on direction. It doesn't depend on where you are. But it does depend on time in general. It may depend on time. Velocity equals distance times Hubble constant. And it doesn't depend on the dimensionality of space. Okay, that's the Hubble law. And as I said, it's an extremely simple idea. Now let's talk about the geometry of space.
Just one question for a minute. And you may get to this later, but this has always bothered me about this sort of thing. So the velocity is proportional to Hubble constant time to distance. This means the distance actually is increasing, so the velocity is increasing. So Bob and Alice are both being accelerated within our model, but neither one of them perceives that.
No. The velocity is not, well, you don't know whether the velocity is increasing with time. What you can say is the velocity increases with distance, all right? But here's a possibility. The velocity of all of these, whether the velocity of a given galaxy is increasing or decreasing relative to us depends on how A is changing with time. For example, let's take a simple possibility. Supposing A was simply proportional to time. The distance between two neighboring galaxies is just increasing with time, with some velocity, some particular velocity. Let's just call it t. Velocity 1 u, right? A was proportional to t. That's just each link here in this lattice of galaxies is increasing linearly with time. Okay? What is the velocity between these 2 points?
dt. Delta t dt. Delta a.
The distance between them is a, and the velocity is just dA dt, which is 1. Well, I don't want it to be 1 because 1 stands for the speed of light, and let's say a half or a quarter t. Supposing A was increasing like a quarter t. That's a perfectly good law. Then the velocity between the two neighbors here is just 1/4, and it stays 1/4 for all time. It doesn't change. But what's the velocity between this point and this point? Twice the velocity between the neighboring points. So it's 1/2. The velocity increases with respect to looking at more and more distant neighbors, but it may or may not increase with time, the velocity. With time, the velocity between any two galaxies. Here's another example. Supposing A increased like t squared. The distance between this galaxy and this galaxy is increasing like t squared. What is the velocity between them? 2t. The velocity is just 2t. In this case, the velocity between these two galaxies is increasing with time. All right? In any case, it increases with distance. Depending on the details of how A depends on time, the galaxies may be accelerating away from each other or even decelerating. For example, supposing let's take another law. Well, let's take the law A goes like e to the minus t. Is that a good law? No, that's not a good law. Okay, let's take log t. Let's take log t. Good, thank you. That was good. Log t. What is the velocity between these two neighboring points? The velocity between them is the derivative of log t, which is 1/t. In this case, the velocity is decreasing with time. As time gets bigger, the velocity is decreasing. That would be saying that they're decelerating relative to each other. So you can have acceleration, you can have deceleration, but always the Hubble law is correct as a function of distance. Okay. That's the basic Hubble law, and it is the basic fact that, that all else is built on. You know, it used to be thought that the universe was decelerating. The reason was very simple. Well, it was thought that gravity was pulling the universe together. If gravity was pulling the universe together, think about it starting expanding, gravity would slow it down, just like gravity slows down this pen as it's going up and will eventually turn it around. It was thought that the universe was expanding, but that the pull of gravity was pulling things back together and therefore decelerating it. That's what was thought to be the case. We now know that that's not the case, and the universe is expanding at an accelerated rate. Okay? Everything is accelerating away from us rather than moving with a uniform velocity. Okay. Other questions?
I got one.
Yeah.
How do you set the initial value of A? I mean, since it's changing.
Well, you pick, yeah, that's a good question, but you pick some particular time. At any time, the initial value of A is somewhat arbitrary. It's not really the initial value of A. It's at which particular time do we set A equal to some particular, or do we measure A? It doesn't matter. You'll always get the same answer. And you might worry about when the particular details, how they affect the Hubble constant. I think what you're asking about is, supposing you called this distance 2A or 3A, would you get a different answer for the Hubble, just by name? You just gave it a different name. Instead of the scale factor being the distance between these two galaxies, let's take it to be the distance out to 1/3 of the way to the next galaxy. We could do that. All right? So we would have another Hubble constant, another scale factor, which was bigger or smaller, it doesn't matter, than our original scale factor, but the ratio of A dot to A would be the same. For example, supposing I defined another scale factor, let's call it B. B is 3 times A. Just another definition for the scale factor, so that it's 3 times bigger than the original definition of it. All right. What about B dot over B? You might get worried. You might think you get a different answer for the Hubble constant, but you don't. You get 3A dot over 3A. And 3's cancel. So what matters really is not the scale factor itself, but how it's changing. That's the important thing, how it changes, not its overall magnitude. But we'll come back to that. It's really a question of units. The scale factor would be different numerically if we measured in meters or if we measured in kilometers and so forth. And it would be different if we chose a different time at which we no, it wouldn't be different. Yeah, what I said is right. Okay, let's talk about geometry a little bit, the geometry of space-time. But first, the geometry of space. The geometry of space and space-time is determined by a metric. The metric, in exactly the same sense as we talked about last quarter. I'll try to be self-contained for those who weren't here last quarter. Let's start with a very simple geometry. Again, a one-dimensional geometry. But for fun, let's change it a little bit. Not the infinite straight line, but let's first consider the infinite straight line. Yeah, we have our coordinate x, and we have that the distance between any 2 points is delta x times a. Let's think of that in terms of a metric. Remember what a metric is. A metric is an expression for the distance between two very close points. When the points are close, we can replace this delta x by the symbol dx. Same thing, except when small magnitudes are small, we replace them by calculus notation. A times dx. That's the distance between two neighboring points. All right? And what's the square of the distance between two neighboring points? Let's call it ds squared. That's equal to a squared times dx squared. Well, that tells us something about the metric. The metric is just the definition of the metric. The definition of the metric of a one-dimensional space, this is a very simple case, of a one-dimensional space, the metric is just a squared. All right, it's the thing that multiplies dx squared to find the distance squared. S here stands for distance, of course, because, wait a minute, S isn't distance, S is distance, spatial distance, ds squared. There's a squared dx squared. Okay. If a is changing with time, then the metric is changing with time. But still, this is just a one-dimensional space with a metric, and that metric might depend on time. Okay? So you see where we're going. We're starting to talk about geometry of spaces. One-dimensional spaces are too simple to have an interesting curvature or anything like that. The metric of space is just a coefficient out here. We could write that as gxx dx squared. And what would gxx be? It would just be a squared. So eventually we're going to want to connect up the idea of the expanding universe with a metric of space-time, but we'll come to that. Let's Good. Now what about proper time? Remember what proper time is. Proper time d tau squared, that is equal to dt squared. This is the proper time along a trajectory. Let's now imagine that what we're talking about is space-time. Let's draw space-time. Here's space-time, x and t. Right. Our galaxies are not changing with x. But wait a minute, they are moving further and further apart, so how can I possibly decide to draw them as if they were all parallel like this? This looks like they're all at the same distance forever and ever. That is where the time-dependent scale factor comes in. Remember that the distance between these neighboring points is not just delta x, it's a times delta x, and that changes with time. Now, what is the proper time along the trajectory, let's say, of a particle between two neighboring points? The proper time, what do we call it, d tau squared? That's equal to dt squared minus the square of the spatial distance between them. What's the spatial distance? A squared dx squared. Right? The square of the spatial distance between these 2 points is a squared dx squared. Not just the x squared, because x isn't really spatial distance. It's just a label which is labeling these points. You could have given them different names, Fred, Harry, Joe, Nancy, whatever you like. But we gave them names which were x equals 1, x equals 2, x equals 3, x equals 4. the fact that x doesn't change for a particular galaxy is the same fact as your name doesn't change with time. That doesn't mean that the distance between you, between Fred and Harry, doesn't change with time. Fred and Harry are their names. The distance between them is governed by both the difference of x and the scale factor a. All right, so here is our formula now for the proper time along a trajectory. It's not just dt squared. Now t here is time measured by clocks moving along here, ordinary clocks moving with this galaxy. If x didn't change, if we were talking about observations along a galaxy, in other words, moving with a galaxy, we wouldn't have any dx squared, and we would just say the proper time was the ordinary time. But if a point is moving through the galaxies from one point to another, then we would say that the proper time is d tau squared minus a squared dx squared. All right, this becomes the spatial distance, and a may depend on time. So another way of thinking about the scale factor is that it's the space component of the metric. Let's just compare that with d tau squared. Well, I needn't compare it. Here's a geometry. It's a space-time geometry. And what is its metric? Its metric, again, is a set of components. The set of components represents the coefficients in this form here. The dt squared has a 1, and the space minus a squared. 0, 0. The zeros represent the fact that in this formula, there could be terms, but there aren't, with dt times dx and dx times dt. So there are no off-diagonal terms. And this is the geometry now, or this is the general relativity description of this expanding space. The general relativity description of the expanding space, going back to last quarter, is that a certain component of the metric, the space component of the metric, is changing with time. That's the way you describe a geometry which is either being stretched or contracted. If the geometry is being stretched, then this component of the metric, we call it gxx. Gxx is minus a squared. It is the thing which changes with time as the universe changes its size, or as the universe changes its scale factor. Scale factor and space component of the metric are the same thing. The same is true in 3 dimensions, or 2 dimensions, or however many dimensions, the only difference being that the metric would contain more terms. Minus a squared dy squared minus a squared dz squared. The x squared plus dy squared plus dz squared, this is just the Pythagorean theorem again, but now multiplied by a squared. So we would have a metric which would have a 1 in the time component, and a minus a squared minus a squared minus a squared, and zeros everywhere else. That would be the metric of an of an expanding space with a scale factor that was a function of time. So another way to say expanding universe or contracting universe is that the metric of space is time dependent. In other words, it's a special case of general relativity metric of space-time where the components of the metric change with time. A growing with time, expanding, a shrinking with time, contracting. All right, so that connects then this idea of the time dependence of the separation between galaxies with the basics of Einsteinian geometry, if you like.
and all three A's in that matrix are the same function because of homogeneity and isotropy?
Good. Let me make a slightly finer distinction. They're not dependent on position because of homogeneity. They're not dependent on direction. All right. The fact that they don't depend on position, moving around in X as opposed to T, they could depend on T, but they don't depend on X, that's homogeneity. The fact that all three are the same, that's isotropy. Okay? That the three directions all look the same, that's what says that these three are the same. The fact that everything is the same from place to place says that A possibly depends on time, does depend on time, but does not depend on position in space. So it's an extremely simple metrical geometry where all of the coefficients are independent of position in space and isotropic, meaning the three are the same, but time dependent. Time dependent, but not space dependent, and not angle dependent, or not axis dependent. All right, now, that, incidentally,
Question.
yeah.
I think I'm a little confused. Are we not supposed to think of dx as a distance?
Yes, dx is not the distance. A times dx is the distance. It's just a label. It labels the galaxies. If you like, here's the way to think about it. There's a bunch of galaxies out there. And at some particular time, it doesn't really matter when, but at some particular time, somebody drew a coordinate grid through them. And now the rule is the coordinate grid follows the galaxies. As the galaxies expand, there's a galaxy over here, there's a galaxy over here, there's a galaxy over here. The coordinate mesh follows the galaxies. All right? That means the distance between here is not delta x. Delta x is always the same between these two galaxies by definition, because this coordinate grid follows the galaxies. Okay? The distance is a times delta x.
That would be the answer in meters or kilometers or something.
Which one? A?
Between two galaxies,
Yeah.
the distance in light years would be a times delta x.
That's right.
As opposed to delta x.
That's right. That's right. Delta x is...
Dividing by c squared, obviously.
Yeah. I'm going to continue to
Well,
call
you could
C1.
put the units of distance into dx.
So
You could put the units of distance into x, but I choose not to. I put the units of distance into a. Yeah. That's arbitrary. That's an arbitrary decision on my part, whether I want to put the units of distance into x or into a. The product of a times x are units of meters.
So should we think of it as a dx squared?
Yeah.
Is that
Yeah, a dx squared. That's the same as a squared dx squared.
Yeah. Yeah.
Yeah. The metric coefficient for time is equal to 1. Is that just by convention also?
That is a convention, not a. There's no physics in that. Supposing I changed it. Let's change it. Now, what is not a convention is that the coefficient doesn't depend on position, but it could depend on time. So let's suppose that it was t squared dt squared, just for fun, okay? Just for fun, let's suppose that we had t squared dt squared. This can be written another way. T dt squared, right? I'm going to put a 4 here just because you'll see why in a moment. That's twice t dt squared. What's twice t dt? It's also the same as dt squared squared. The differential change in t squared is dt squared. In other words, whatever is here, it can be written, how to say this right, you can always change variables. Given a thing like this, you can always change variables to a new definition of time where this becomes just dt squared. If it's not dt squared, you can find a new change of variables, of time variable, where it becomes dt squared. Yeah?
I think there's another possible question about whether there should be c squared dt squared.
Oh, yeah.
You're using c.
Well, I would put the c squared over here.
Or put it over there.
Yeah. But you can also absorb it into the scale factor. You can absorb it into the scale factor if you like. So that's a, but my rules are going to be c equals 1. 1 light year per year. Okay? That's the speed of light. 1 unit in light years per year. Light years per year is not such a bad unit for astronomy.
If you put this into Einstein's general theory,
Yes.
Field equations,
Yes.
What do you get for the energy momentum vector?
Well, so far, wait, be careful. All right. A couple of corrections. Energy momentum tensor. Yeah, no, that's a good question. And this is something we're going to spend a lot of time with, so let's not do it now. That's right. Right. This is a metric. You could say, you can put it into Einstein's equations. Remember that Einstein's equations have on the left-hand side something that involves just the metric, and on the right-hand side has the energy momentum density, or the mass density, or whatever, energy, momentum, mass, all the same stuff on the right-hand side, energy and momentum. So if we put in this geometry, we could calculate what kind of energy momentum distribution we would have to have in order that it solves Einstein's equations. So we're going to come to that. That's a very important part of the whole thing. But for the moment, for now, we're just doing geometry and not dynamics. Dynamics is what determines how the metric changes with time. Geometry is just the abstract description of a space, or space-time. Okay, so an expanding universe is one where the space components of the metric change with time, and given the homogeneity and isotropy of the universe, A is not a function of position, and it doesn't depend on which direction we're talking about. That's basic. Rules of cosmology, and they're not absolute rules in the sense that one could discover, it's inconceivable that one will discover that the universe is not isotropic. In fact, it's not exactly isotropic. It's certainly not exactly isotropic. In different directions, you actually do see slight differences. It's certainly not homogeneous. It's not the same here as it is a light year away from here. So it's certainly not exactly homogeneous. It's not exactly isotropic. And we could discover, in principle, that the universe is fairly far from isotropic and homogeneous. Thus far, we've made no such discovery, and I think it's unlikely that we will, because I think we've seen about as much as the universe as we're ever going to see. The universe is bigger than the portion we can see, and it's bigger than the portion we can ever see. So we don't know that on distance scales bigger than we can see, we obviously don't know very much. We don't know if the universe is homogeneous, isotropic on those very large scales. But it has turned out that over the size and scales of the universe that we can measure astronomically or by whatever means, the universe is isotropic and homogeneous, apart from local variations on small scales. You know, it's kind of like a farmer's field. If the farmer has planted his corn well and accurately, then on a scale of 100 feet, it looks pretty homogeneous, equally spaced rows and so forth. On the scale of 2 inches, it's very non-homogeneous. And on a big enough scale, namely a scale bigger than the whole farm or the whole field, it's again not homogeneous. What we know about the universe is that on scales between distances between galaxies, 100 galaxies apart or so forth, that out to scales as far as we can see, the universe is homogeneous. We don't know whether it's homogeneous on bigger scales, and we probably will never directly be able to find out. Okay, let's come now to closed geometries.
You said you never directly find out. Does that imply you think there might be an indirect way to find out?
Well, perhaps. I think most thinking these days is that it's not homogeneous on big enough scales. But that's certainly something we'll talk about before we're finished. My bet very strongly is the universe is not homogeneous on large scales. But I will never win my bet, but I will also never lose my bet.
Well, but then you could write a book.
I can only write a book if I win my bet. Or lose my bet. I mean, I'd be willing to write a book if I'm losing a bet. That book won't be written because for basic fundamental reasons, we won't be able to see much further than we can see now. That's called the existence of a horizon. It's a problem.
Couldn't you derive the idea from gravity to look at massive beyond what you can see?
No way to tell what's out beyond what you can see.
So even the gravitational force would be limited by c?
No. If we're sitting here in this room, we are in the field of the sun and we're circulating around the sun. But there's no easy way, there's no way for us in this room, on this earth, without being able to see out beyond the room, to tell that the sun is there. Now, we can measure tiny tidal forces, but the tidal forces in this room, I don't feel stretched. Do you feel stretched? I'm not talking about the tidal forces due to the Earth. There's certainly tidal forces due to the Earth. I feel, I actually can't feel those either. If I jump off a springboard, a diving board or something while I'm in free fall, I don't feel squeezed and pulled, and I can't tell that the Earth is there. If I close my eyes, I could be in free fall a zillion miles from the Earth. So the answer is that you can't tell that there's a large mass out there except by its tidal forces. It only has tidal forces if it's close enough to you and you are big enough to feel the variations of the gravitational field from place to place. So if there's a large lump of mass very far out there, we're just freely falling in the presence of it, and we don't feel it except, I say, through possible tidal forces, which are too small to feel if things are far enough away. Right, so the horizon, which we haven't even begun to discuss yet, is an ultimate barrier to... And the frightening, I don't know if it's frightening, frustrating, frightening, fascinating thing is we know with virtual certainty that the universe is at least 1,000 times bigger in volume than the horizon, than we can ever, in principle, ever see. So we know the stuff out there that we will never be able to detect. And we can't tell what it is, we can't tell if it's similar to us, we can't tell...
Why do you know that?
That's why you took this course, to find out. Microwave anisotropy. The measurement of the curvature. But if I don't answer that, remind me to answer it, but not now. Okay, let's talk about the idea of a closed universe. Now, the closed universe, well, it's best described by example. The infinite line is an open universe. Closed and bounded. I'm not sure. Closed and bounded. Closed and bounded. The infinite line is certainly not bounded. A line segment like that is bounded. Only has a certain size. Bounded means it has boundaries. It comes to an end. Well, that's not what bounded means, excuse me. It doesn't mean that it has boundaries. It just means, in some sense, it's a finite extent. Now, the universe is not, as far as we know, anything like this line. It doesn't have to be a line. We could be talking about a square or a cube. A cube with walls. The universe could all be inside a cube with walls. What does this violate? It violates homogeneity. Every place is not the same as, and isotropy for the case of a cube. Yeah, and isotropy. Somebody standing right at the center sees something quite different than somebody standing up here near the corner. Number one. Number two, even at the center here, even if you are at the center, you look in different directions, you see different things. In one direction you see a corner, in another direction you see a smooth face. By see, I mean detect by whatever means you can detect the shape of the universe. So a bounded universe seems like it's out of bounds in the sense that if the universe is truly isotropic and homogeneous, then let's concentrate on homogeneous. Then it can't be a cube with walls. Good. Okay, so a sphere is a very interesting case. Here's a sphere. The circle is good enough. I mean, the interior of the circle. We have this region in here. Somebody at the center looks out in different directions and sees the same thing in every direction. So from his perspective, or her perspective over here, the universe appears isotropic. All right? But it's certainly not homogeneous. Somebody over here does not see the same thing as somebody over here. This person over here sees a wall close to him on the right, or upper right here, and far from him in the other direction. In fact, this observer over here on this galaxy does not see an isotropic universe. Doesn't see an isotropic universe because the direction is different than that direction. It's neither. It happens to be isotropic for one special person, the person at the center. But for everybody else, it looks non-isotropic, and it's certainly not homogeneous because the properties over here are different than the properties over here. All right, so that boundary is we don't know, as I said, that the universe is truly on very, very large scales isotropic and homogeneous. But let's take it as a principle. In fact, it is called the cosmological principle, that the universe is isotropic and homogeneous. Now, I remember as a young physicist being absolutely convinced that it must be true because it's a principle. And then when you ask, where does this principle come from? Well, we assume it's true. So it is the cosmological principle, but it could, any day of the week we could make some radical discovery that it is not true. I don't think it's going to happen for reasons that you'll understand later. Yeah?
Does isotropy everywhere imply homogeneity?
Yes, that's a good point. Isotropy everywhere implies homogeneity.
In other words, isotropy is homogeneous. In other words, its isotropy is homogeneous.
If the universe is not homogeneous, then somebody will see it being anisotropic.
But if it's homogeneous, it doesn't mean it's isotropic.
No, that's right. That's right. For example, here is a universe. This is a universe of arrows. It's a universe made of arrows, and they're all pointing in the same direction. They densely fill space, let's say. that's very homogeneous. This goes on and on and on. It's homogeneous in that it's every place the same, but it's not isotropic. It has a direction associated with it. Right. And isotropy doesn't imply homogeneity. This fellow at the center here sees isotropy when he looks out, but this is not homogeneous. But if everybody sees isotropy, if everybody sees things being the same in every direction, that happens, yes, to imply homogeneity. So they're not quite independent. They're two different concepts. They're related, though, in a particular way. Yeah?
So if you're on the surface of the sphere.
Ah, the surface of the sphere. That's another thing. On a very bald sphere, bald meaning featureless, every place is the same as every other place. Every direction that you look in is the same as every other direction that you look in on the surface of a sphere. And it's bounded. Remember, bounded does not mean that it has a boundary. Now we're talking about little creatures. Let's imagine little two-dimensional creatures, flatland creatures, except instead of living on a plane, they live on the surface of a perfect sphere. And they can't look away from the surface of the sphere. They can't look into the sphere. And the reason is because light only travels on the sphere itself, on the surface of the sphere, in this theory, or in this world. If light only travels on the surface of the sphere, all they can do is look around within the surface of the sphere, look that way, that way, that way, that way, and on the surface of the sphere, all directions are the same and all places are the same. So that's basically the key to combining isotropy, homogeneity, and boundedness. Again, boundedness does not mean a boundary. These creatures do not fall off the edge of the earth when they get to a certain point. They go around. So boundedness does not mean boundary. It means boundedness. Finiteness in some sense, right. Okay. All right, the simplest example would be life on a closed curve. For example, life on a circle. Okay. A circle has a metric. Let's talk about a life on a circle. A nice parameter which could be a coordinate. Again, there might be galaxies sprinkled around on this circle. Every point on the circle is the same as every other point. Not quite true, of course. The points between the galaxies are different than the points on the galaxies. But on scales bigger than the size of a galaxy, every point is the same as every... Incidentally, what does isotropy mean in one dimension? Isotropy is clear in two dimensions. You look in different directions. What? Left and right being the same. That's right. So here, for example, is a one-dimensional world which is homogeneous but not isotropic. It consists of little arrows pointing in one direction all along it. Left is different than right. Right? Left is different than right, but every place is the same as every other place. So in a one-dimensional world, you can also have anisotropy, non-isotropy. What it means is simply left and right along the line are different. Okay, so if I just have a population of galaxies like this, on the average, left and right are the same. Every point is the same as every other point. And I would say this was homogeneous, isotropic, and bounded. Okay. Let's talk about the metric. Let's talk about its geometry. What might we characterize the position by? Well, we could use x, but x is an inconvenient variable on a circle. A convenient variable on a circle is angle. So we could pick one galaxy and call it theta equals 0. Theta is my notation for angle, or at least one possible notation for angle. And we could characterize every other galaxy, this is theta equals 0, by some theta. And what's this galaxy over here? Well, we could call it minus a negative angle, or we could call it 364 degrees. All right? It's almost all the ways around. So, what did I say? 300? Did I say 364? Oh, that's the number of days in a year. Gee, 365, 359. Sorry, I got the number of days in a year confused with the number of degrees on a circle. Wow. Okay, right, 359 degrees. Not quite all the ways around, not quite 360 degrees. Okay, but we could use an angle to characterize the position. Right. Again, all right, let's suppose for the moment that the radius of this circle, or the circumference of it, the little bugs who live in this world, have no sense of radius because they have no sense of where the center of it is. It's not in their world. But they do have a sense of circumference. They can measure the circumference by marching along it till they come back to the same place. They can measure the circumference. The circumference means something. And of course, they could call the circumference 2 pi times something if they wanted. And that's something they might call the radius, but they would have no particular reason to, but they could. So they have a sense of circumference. And let's now talk about the distance between, the distance around the circle, the size of the circle. We can call, let's see, let's call the total distance around the circle. Do I want to call it A or do I want to call it 2 pi times A? I think I'll just call it A. Scale factor. Scale factor is the total distance around. Now, supposing we have, yeah. Why am I calling that scale factor? We'll see in a moment. But let's take the distance between 2 points, theta equals 0 and theta equals theta, just theta. What's the distance between those 2 points? A times theta. Let's define it to be A times delta theta. A is not, let's see, we got to do this right. Let's get the numbers in there correctly. We're going to measure angles in radians. All right, so the total distance around in radians is 2 pi. Total distance around is 2 pi. So this point is 0, and if I go all the ways around and I come to the point just below it, that's 2 pi radians around. Okay, the total distance around is 2 pi, let's call it 2 pi times A. I'm going to call it 2 pi times A, where A would be the radius if I decided to plot it as a circle. If I decided to plot, now remember, these people who live on here can't tell whether it's a circle or whether it's a curve like that. They have no way of telling because they can't see into the interior. All they know is the distance around. But let's pretend that we drew it as a circle. Then the total distance around I would call 2 pi times A. But what's the distance between 2 neighboring points? Let's suppose the points were separated by a distance delta theta. Then the distance between them would be A times delta theta. The radius of the sphere, the radius of the circle times the change in angle. The distance between 2 points on a circle of radius A, is A times the angular distance. Well, this is very much like A times delta x. It's just I've used theta, and theta happens to have the property that when you go around the circle, it comes back to itself, that you come back to yourself. But otherwise, this is very much like A times delta x. In fact, we have a metric. We can say the distance between 2 points squared, between two neighboring points squared, is a squared d theta squared. So in fact, we have a metric on a circle, very, very similar to the case of the infinite straight line, except now the space is bounded. It's bounded because when theta comes all the ways around by 2 pi, you come back to the same place. This is a closed and bounded universe, and here is its metric. Now, this is not a space-time metric, this is just a space metric. Right? So you could imagine the creatures who live on this thing measure this distance around here, and then they know what A is. They know what A is. Okay? But you can also imagine A changing with time. Again, A changing with time would correspond to the radius of this circle changing with time. In that case, we would write ds squared, distance between 2 points, is a of t squared times d theta squared. And we might even write a space-time metric. We might write d tau squared, the space-time metric, is dt squared minus a squared, a of t squared, d theta squared.
That should be a squared, t squared in the first of the lineup from the second.
No, not here. No.
One up above that. A squared.
Of t squared. A squared. A of t squared. Good. Yeah. D theta squared. Good. Yeah. Yeah. Right. All right. What does this geometry look like? Let's try to think about it as a space-time. As a space-time. We'll start. The vertical axis is going to be time. Let's start at one instant when A has some particular value. Here's A, let's say A equals 1 or 7 or something else. So it looks like a circle. That's at one particular time. Now the vertical axis is the time axis. As time goes on, A changes. That means, let's say, it gets bigger. That means that the space-time geometry grows with time. Let's suppose at some time it stopped growing and turned around and shrunk, started to shrink. Turn around and start to shrink. Maybe it does something crazy, oscillates, starts to grow again. The surface, the space-time looks like a surface, and it looks like a surface of a, it looks like a vase or a vase, whatever you call it. In fact, we might even imagine a space-time which starts, what would the scale factor be at this point? If the universe started infinitely shrunken. Here it is. It starts infinitely shrunken, like a circle of infinitely small size, and it starts to expand, expands out to some maximum size. I'm not taking this as seriously that it expands out to maximum size. Expands out, starts to shrink again, starts to grow again, does whatever it does. What would be the scale factor at this point? It would be A equals 0 at that point. So in this closed and bounded universe, A equals 0 corresponds to the thing shrunk to 0 size. Right? And then it starts to grow. It grows from 0 and very quickly becomes something not 0, and then changes its size, maybe in and out and in and out, whatever it does, whatever it does. Okay, so that's a geometry. It's quite clear that this geometry is curved. It's quite curved. It's curved in the sense of Einstein. That's a closed and bounded, this is the simplest example of a closed and bounded universe, which also happens to be time dependent. In this universe, Hubble's law is still correct. for exactly the same reasons as before. The distance between 2 points again involves a times delta theta. Distance is a delta theta. The velocity is a dot times delta theta, and that's the same as a dot over a times a delta theta, which is Hubble constant a dot over a times distance. So Hubble's law is still true. The velocity between these points is proportional to the distance between them. You get into a little bit of confusion when the distance is so large that it comes around the other side. Let's forget that for a moment. But an astronomer over here looking not too far away would see Hubble's law. And that's the idea of a closed and bounded universe. Okay. Notice that the closed and bounded universe is not an explosion from a point in three-dimensional space where stuff gets ejected out. It's not like the explosion of a hydrogen bomb where something is concentrated in space and then goes flying out into space. It's the same everywheres. Everywheres it's the same. And yet, if we imagine galaxies, let's imagine galaxies or particles or whatever. Here they are, they're spread out on here. They separate because the distance between them gets larger. They start to come together again. They start to... What happens to them when we look way back at very early times? They're very close to each other now. Let's say there are 360 galaxies. Those 360 galaxies are well spread out here, but they're very, very close together here. Here they're even closer together. They get too close together, they're not separate galaxies anymore. Get them even closer, they're not even separate atoms anymore. But notice, there's no special point in space. Space now does not mean this three-dimensional room. It means this one-dimensional closed and bounded universe that little bugs live on. No special place, no sense of being ejected out of some particular place like the bomb explosion, but instead just a uniform, rapid expansion taking place everywhere at the same time, satisfying the Hubble law. Okay? But things get pretty crowded down here. Infinitely crowded if the universe began as a point. So when somebody comes and asks you, well, where did the Big Bang take place? Where did this Big Bang take place? Where were all these things ejected out of? The answer is everywhere. Okay, so question.
Is this, you said the space-time is curved. Is it curved if that was a cylinder?
Say it again?
You say the space-time is curved. Would it be curved if that were a cylinder?
No. If it were a cylinder, it would not be curved. If it was a cylinder, in other words, if A were constant with time, if A were constant with time, that would be like this. That would be this world. Oh, good. A cone is an even, yes, good, cone. All right, first of all, cylinder. A cylinder is the case where A doesn't depend on time at all. Right? Good. That's just a constant A up and down. That is not curved. That's not curved. That's obviously not curved. No, the cylinder, the space-time is not curved. It looks like it's curved because I tried to draw it in 3 dimensions, but it's not curved. Remember why? You could take a scissors and cut it open. Take a scissors, cut it open, without stretching it, you could lay it out as on the plane. And it would be, you don't have to stretch it to lay it out on the plane. Okay, so that's not curved. If you laid it out on the plane, so there it is. I've cut it open, laid it out on the plane, just mathematically cut it open in my imagination. Then the cylinder is in here. But this point and that point are the same point in the sense that when I cut it here, this point, which half of which went this way and half of which went that way, become these 2 points, which are really the same point. All right. So no, the cylinder is flat. Okay? Or equivalently, in this particular case, for a one-dimensional universe, not the same, the three-dimensional is different, but for a one-dimensional universe, the time-independent universe is flat. Okay, flat in the space-time sense. Now, what about the cone? First of all, what does the cone correspond to? It corresponds to, there's the cone, the space-time cone. How does the scale factor grow with time in the space-time cone? Linear. Linear. The size of the cone is linear in the time. And you double the time, that means double the distance along here. You double the size of the, all right, so that means A is proportional to time. Again, a quarter, a fifth, a tenth, whatever. The scale factor is proportional to time. Is this or is this not flat? As a space-time, it's not flat at the bottom, that's for sure. It's got a conical singularity there. But cones, if you slice them and open them up, are flat. All right, so a cone is flat. You make a cone out of a flat sheet of paper by, it's the same deal as we studied last time. Just by sewing the edges together, you make a cone, but the only place that the cone is curved is right at the tip of the cone here. That's the only place where there's any real curvature. So yeah, this is also flat except for the tip. The tip is the origin of time here, the Big Bang or whatever. We haven't gotten the Big Bangs yet. All right, so I think it's time to quit now. Next time we will discuss not the circular universe, but the spherical universe, or the universe which is a three-dimensional sphere, and the geometry of it. And then we'll go on to discuss what is the thing which determines how the universe grows. What is the dynamics which causes it to grow or shrink or whatever it does. And that will bring us to the end of next week.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.